Alright guys, today we're going to take a look at a very interesting problem. Alright, so here we have a double pulley, and they spin together rather than independently. And has two components. Small component have a mass of m3, has a radius smaller. Bigger component has a radius of bigger, a mass of m4. Now you have the two masses attached to the double pulley like this. So to approach this, usually the first thing we ask is, what's happening? What's the acceleration? And or more importantly, what's the direction of the acceleration? So let's see. So the first one we're going to explore is one. So when the masses are just released, which way are the masses going? Okay, so we know that when it just starts on rest, we can pretty much disregard the value of the acceleration. So we can pretty much say that if I give this t2, this t1. I can pretty much say that at this moment, m2g is t2 and m1g is t1. Okay? Then we can say, let's sum the torque about the pivot points. So remember, stick to convention. So counterclockwise is positive. So T2 big R, and clockwise is negative, minus T1 R. Smaller, and this is M2G R minus M1G R. Okay, so if you're given the value, if you have a value to plug in, then you can figure out which direction, counterclockwise or clockwise, is this thing going. So once we figure out, what's the direction of the acceleration. So here, let's just say, given arbitrary direction. So let's just say it's going this way. Okay, so it's accelerating counterclockwise. So the next problem we ask is, what is the value of the acceleration? Okay. So in the previous videos, when we analyze the situation, we say, analyze the linear behavior and the rotational behavior, and we, plug in, express one quantity using two ways and plug them in and get the acceleration. So here it's pretty much the same idea, but one thing we have to note is that the acceleration is not the same for the double pulley and the two masses, but the angular acceleration is the same, because if you see this, so they move together, but they move on different radius. Okay, so obviously their acceleration is going to be different, but their angular acceleration, in other words, if they start from rest, the angular velocity for two masses are going to be the same. So here we really try to find first the alpha, the angular. So similarly, we apply the linear behavior and the rotational behavior to this system. So let's see what can we do. So first, M2, I think this is extremely basic for us. Just do the sum of the forces. Put MA, then M2G minus T2 is equal to M2A. Okay, so that's M2. M2. M1 is pretty easy as well. The stuff we've been doing a lot. So T1 minus M1G is equal to M1. Okay. So the thing that is a little bit complicated will be the rotational behavior. So we know that they spin together, so we can regard them as one body. In other words, the moment inertia of the one body is a summation of the moment inertia of the two components. So let's just say they are disks. Okay. Then we know that I total, right, the total moment of inertia is 1/2 m3r squared plus 1/2 m4 big R squared. Okay, so that's the total moment of inertia, because they spin together, so we regard them as one body. Okay. So for our simplicity's sake, let's just call this I total, so that the equation we obtain will be more clear. Okay. So now we can put them together. We still need to sum the torque. So sum the torque is I alpha. Well, this is just T2 minus T1 is equal to, just call it IT times alpha. Okay, so we know T2, we can express T2 and we can express T1. So let's plug them in. So here I got T2 is M2 G minus A, and here I got T1 is M1 A plus G. Okay, so what I really get here is So T2 is this, okay? So M2G into parentheses R minus M1 A plus G small r is equal to I alpha. So here we need just do a very quick conversion to convert everything into alpha. Okay, so RM2 G minus alpha. M2 is on the bigger component, so AR minus RM1 alpha R plus G is equal to I alpha. Okay, so now we can finally solve for alpha. So here we get R M2G minus R squared M2A minus R squared M1 alpha minus RM1G is equal to I alpha. So clean this a little bit, so we get what RM2G minus RM1G is equal to I alpha plus R squared M2 alpha plus R squared M1. So here we have alpha I plus R squared M2 plus small r squared M1 is equal to this. So eventually we have RM2G minus RM1G divided by I plus R squared M2 plus R squared M1 is in fact alpha. So you looking at this, if you're given the total moment inertia of this double pulley, then once you know the mass of two masses and the radius, you can solve for alpha. If not, you have to be given the individual masses or the combined mass of both, or the total mass of both. Okay. So yeah. So looking at this. Yeah, so looking at this, we can see that this is RM2G minus RM1G is similar what we obtain here. Then the bottom, yeah, not much to say at the bottom. So know the idea here, okay? So the two linear behavior and the one tweak here, as opposed to other stuff, is you regard this as one body and solve it from there. Okay, I hope you guys can find this video helpful, and I will see you next time.